In our final video in the solubility equilibrium section, we're going to look at how to predict whether a precipitate will form given a set of starting conditions of two different solutions. So the first thing that we'll need is to figure out what our precipitate is going to be, assuming that we mix a solution of sodium chloride with a solution of silver ions. Well, we know from sodium chloride, because all alkali salts are fully soluble, that the sodium and chloride are going to fully dissociate into sodium and chloride ions, and since sodium ions can't react with another cation, they're not going to be important, which means that our precipitate is going to form from the silver ions from our second solution reacting with the chloride ions from the first solution in order to give us the precipitate AgCl. From here, we can write our KSP expression, which is simply the concentration of Ag plus times the concentration of Cl minus, and if we go to our KSP data table, we can find that the KSP value of AgCl is 1.8 times 10 to the negative 10, so let's write that here for reference. Now, in case the title of this lesson didn't give this away, the calculation that we're ultimately trying to do is comparing our KSP value with Q, which of course is our reaction quotient. And remember that the reaction quotient, which again we use the variable Q, is meant as a KSP calculation, but where we don't know whether our concentrations are at equilibrium or not. So what we're trying to find out is how our concentrations of silver and chloride ions compare to KSP and how we can use this information to predict whether a precipitate is going to form. So let's go ahead and do our Q calculations. A lot of people may make the simple mistake of taking the Ag plus concentration that we have here, forgetting that we actually mix two different solutions together, meaning that the volume of our solution is going to change, and therefore our concentration is going to be a little bit lower. So if we do these calculations here, let's write our initial concentration of silver, 6.0 times 10 to the negative 5 moles of Ag plus per liter, and we're going to find out how many moles we have by multiplying by the starting volume of the silver solution, which is 0.0050 liters when 5 milliliters is expressed in liters. And then we divide that by the total volume of the solution. 10 plus 5 is 15 milliliters, which we would write as 0.015 liters. And that is our concentration of silver, taking the volume change into account. To find the concentration of chloride is a little bit more complicated because we're given a mass measurement. And for those that haven't memorized the molar masses of sodium and chloride, don't worry, I've taken care of that for you. Just make sure to check my arithmetic and make sure that I can still add properly, and there we go. So what we need to do to find our moles per liter of chloride is take our starting mass of sodium chloride in grams, and then we're going to convert this into moles by dividing by our molar mass, 58.44 grams per mole. And then if you want to be completionist about this, we can say that we have one chloride ion for every unit of sodium chloride, but remember this is just multiplying by 1. And to get this in moles per liter, we need to divide this by the volume of the overall solution, which is 15 milliliters. And once we've done that, we've found our concentration of chloride ions, which we then multiply by the concentration of silver ions. And if you put all of this into your calculator, you'll find that your answer comes to approximately 5.7 times 10 to the negative 11. Now here's where we need to remember our comparisons of Q versus KEQ from the previous section, and we can see here that our Q value is quite a bit less. It's more than a full order of magnitude less than our KSP value. So what this means is that Q is less than KSP. Well, if we remember the comparisons with KQ and KEQ, remember that KEQ is simply a measure of the concentration of products divided by the concentration of our reactants. So in this case, we don't really have concentration of reactants because our precipitate is constant. So comparing Q and KSP is effectively telling us whether we have too many products, too few products, or exactly enough products in order to be at equilibrium. So in this case, if Q is less than KSP, that means that our concentration of products is too low. And if the concentration of products is too low, that means that we don't have enough ions in solution in order to be at equilibrium, and therefore our solution is unsaturated. And if our solution is unsaturated, that means that we can dissolve more ions into our solution, and therefore we're not going to see any precipitate form. So because Q is less than KSP in this case, we would expect that no precipitate is going to be visible in this particular solution. But what about in the situations where Q is equal to or greater than KSP? Well, where Q is equal to KSP, our concentration of products is exactly at equilibrium. So therefore, our concentration of products is at the saturation point. And remember that the saturation point is exactly where the precipitate begins to form. So at this point, we can say that our precipitate is actually going to appear right when we are at the saturation point, when the concentration of products is exactly equal to what KSP would say they would be. Now, if Q is greater than KSP, that means that our concentration of products is too high, which means that our solution is definitely fully saturated, which means that we cannot dissolve any additional ions within our solution, which means just like at the saturation point, we would expect that the precipitate is going to appear and be very clearly visible. But as mentioned before, since our Q value is less than our KSP value, we would expect that this particular solution is unsaturated and therefore no visible precipitate would be present. In the next series of videos, we're going to look at how to apply the concepts of dynamic equilibrium to closely related equations involving acids and bases.